So let's go ahead and get started with this one. I kind of crammed two sections into one set of notes here, and both of them probably could have been taken individually, but now we're in a hurry because I need to get you guys to the end of the year where we're reviewing. So the concepts here are not that difficult. We're just introducing some new equations, so hopefully this will be all right. So first I want to talk about spontaneity and how that relates to redox reactions. Okay, we can actually look at the voltage and it tells us something about spontaneity, which in the lab that we did yesterday and we'll do again today, you can kind of see that. If you connect the, or if you set up your cell in a certain way, you're going to end up getting a negative voltage and nothing happens. The reaction does not happen spontaneously in the forward direction. Okay. If you set it up correctly, you should get a positive voltage. And anything with a positive EMF, that's a spontaneous reaction. Okay, so positive E is going to tell us that a reaction is spontaneous, just like negative delta G told us in the last chapter. Okay, so that's kind of the idea here. And I messed up. So it says any reaction that occurs in a voltaic cell to produce a positive EMF will be spontaneous. Therefore, if a reaction produces a positive EMF, it will be non-spontaneous. Then you change that on your notes to negative. Yeah. So a negative EMF will be non-spontaneous. I think when I wrote that, I was thinking delta G, so it's positive there. Sorry. So we can write the EMF equation in a little more general way. Instead of writing anode and cathode, because that's language that's specific to a voltaic cell, we can actually, calculate the E of any redox reaction if we just take reduction process minus oxidation. Okay, and the cathode is where the reduction is occurring, the anode is where the oxidation is occurring. So it's basically the same reaction, it's just renaming our terms a little bit. Okay. All right, so let's look at a couple sample problems here. Using our standard reduction potential chart, which you probably will need that out again for this set of notes, because we're going to look at that a few times. So the standard reduction potential chart, we're going to determine whether the following are spontaneous under standard conditions. Now, these aren't voltaic cells. These are just, we're actually putting the solid copper into an acidic solution. Okay. You might already know what the answer to this one is. Just by looking at it, if we put copper into an acidic solution, we've done that already this year. We even talked about that just on the last set of notes, I think. What's going to happen? Okay, hydrogen gas would form if the copper does react with hydrochloric acid or whatever else. When we built a copper cage for our magnesium in that lab, did the copper react with the hydrochloric acid? That's why it was the cage, right? Okay, because it didn't react. So, you put copper into an acidic solution, it's really not going to do anything, right? But let's go ahead and calculate it to prove that, all right? So if we want to find the E of this cell, or just the E0 here, we're going to assume that we're at standard conditions because they're saying we're at standard conditions here. What we need to do is figure out which one is the oxidation, which one's the reduction here. Okay, what's the reduction process? Because that's the one that has to come first. Which one's being reduced the way that the equation is written here? The hydrogen, right? Okay, so if we look on our chart, or just remember something, the reduction of hydrogen is 0 volts, right? That's the standard. 0.00, yeah. Okay. Minus the reduction potential of the oxidation process, which is the copper going to copper 2 plus. Okay. Copper going to copper 2 plus is 0.34 volts. Okay, so you can see here when we subtract those two, we get a negative number. Well, negative number means it is non-spontaneous, okay? So that just confirms what we thought we knew here. Copper does not react with H plus ions to form copper 2 plus. Okay. The next one down here, chlorine plus 2I minus. Now again, I think we have done this reaction already in a previous example. But we can now use the E0 concept to calculate whether this thing is spontaneous or not. So, what is the reduction process in this reaction? Say it again. Okay, the chlorine is going from a 0 oxidation state to a -1. Okay, so that's gaining electrons, that's being reduced. So our reduction potential for chlorine is 1.36. It's pretty high up there on the chart. Minus the oxidation process, which is the I minus going to I2. And that one, if you look a little bit further down the chart, is 0.53 volts. Okay? So when you subtract those from one another, which I should be able to do in my head, and I'm doing it in my head right now. I promise. Actually, I was lying, I'm sorry. 0.83 volts, okay? That's a positive voltage. So if that's a positive voltage, that tells us that this one actually is spontaneous. Now again, you probably could have figured that out in a couple other ways, or at least one other way. And the other way you could have figured that out is the chlorine is gaining electrons here from the iodine. If you look on the periodic table, chlorine is higher than iodine, so it probably has a higher electronegativity. So the likelihood of this taking an electron from the iodine is pretty good. Okay. But again, we're just confirming it with numbers here. All right. So how does the activity series relate to reduction potentials of various elements and ions? This is slightly unnecessary because you're never going to need, I don't know, I say you're never going to need the activity series on the AP exam. You did have one free response question we went over the other day where it asked you to list the metals in order of their increasing or decreasing reactivity. I can't remember which. What you need to know about the reactivity of metals, they're considered to be more reactive if they tend to give away electrons more readily. Okay? That's kind of the opposite of this chart, right? So on this chart, the standard reduction potential chart, what is the most reactive metal listed on this chart based on the reduction potentials? Okay, actually cobalt would be the least, well, cobalt 2 plus going to cobalt 3 plus would be the least reactive, right? Because that's the one that has the highest tendency to be reduced. The lithium, right? Okay, you guys see that? Because the lithium's at the bottom of the chart. So lithium is the one that has the highest tendency to be oxidized based on these reduction potentials, okay? So the activity series is kind of the reduction potential chart flipped, if that makes sense. Okay. Now that doesn't work out perfectly all the time. Okay, there are exceptions, there are reasons why it doesn't, but that's a pretty good general rule. Okay, so if you have this reduction potential chart, you kind of have an activity series as well. Okay, so I just wanted you to be aware that if it's asking you what's the most reactive metal, magnesium or copper, it's fairly easy to see on this chart. Magnesium is way further down the chart. Okay, it has much lower reduction potential than the copper. So we would say magnesium is the more reactive metal. Okay, it's the one that has the higher tendency to be oxidized. So that's kind of how that works. Now I'm not going to write anything up here. I just wanted to talk about that briefly, just to make that connection between what we did last year and what we're doing this year. Because this year we're kind of looking at it from the opposite side of the coin. All right. So, EMF and free energy, let's relate those two to one another. Because we said that both of those things can be used to indicate whether a reaction is spontaneous or not, we can relate them in an equation. Okay, so here's the equation, delta G equals negative NFE. And I believe this is on your equation sheet. I think it's under standard conditions, so this would be delta G0, delta E0, or just E0, which we'll talk about in a second. Okay, but that's the reaction. Delta G is the Gibbs free energy. The N there is the number of electrons that get transferred in the reaction. Okay, we've had a couple practice problems already where we've had to figure out how many electrons are being transferred during the course of a reaction. So that comes in handy here, because now we can plug it into this equation. Okay, Faraday's constant is the F, and that's just 96,500 coulombs per mole. Okay, so that's basically the equation that we need to relate those two things to one another. And then obviously the E is EMF. Okay. Why is the NFE expression negative? What do we think here? Okay, for a spontaneous reaction, delta G is negative. For a spontaneous reaction, E is positive, right? So because those two things have opposite signs when they're spontaneous, to relate them to one another, the two sides of the equation need to have opposite signs. Okay? Here's the equation, I believe, that is on your equation sheet. Okay? So that's just when they're in their standard states. That's when we have a 1 molar concentration, we have 1 atmosphere of pressure and 25 degrees Celsius, or 298 Kelvin. Okay? Alright, so use the standard reduction potentials to calculate the standard free energy change, delta G, for the following reaction. Okay? So what we can do here, since we've got this equation, we can actually find the E using the standard reduction potentials. The N and the F we should also be able to find using that equation, and then we can solve for delta G that way. Okay, so that's just another alternative. It's another way to solve for delta G. So the first thing we have to do is we have to figure out the E0 here. Okay? So remember, the E0 is the reduction potential of the reduction process first, okay, minus the oxidation process. So what's the reduction process in this particular reaction? It's not going to be the oxygen here. Oh, I'm sorry. Yes, it is. Yep, my fault. Yep, sorry. So that's going from a 0 to a 2 minus, right? So that's getting reduced. Yeah, I apologize. Okay, good job. Alright, so 0 to 2 minus, that's the reduction, that's the oxygen. Now, this one's a little bit tricky because I'm looking for that on your chart, although actually it's not that bad on this one. It really matches pretty well with something that's written on your reduction potential chart. Do you guys see it? The oxygen plus 4H plus 4 electrons. Okay, that looks very similar to the half reaction that we would have here. Now, if you want to, you could actually, and maybe it's useful to do this just for a little bit of review. I really hope we have time for this. We'll do it fast. Okay, so one of the half reactions here is the O2 going to H2O, right? Now, we have to put a 2 here to balance our oxygens, but that means we have to put 4 H's on this side, 4 H pluses on this side. And again, we can assume this is an acidic solution because they have H plus in the overall balanced equation. Okay, that means there needs to be 4 electrons over here. Oops, ran out of room. That's a 4. So, I don't know why I started that so far to the left, because I had plenty of room on the other side. But that looks very much like the equation, the half equation that they give you here on the reduction potential chart, right? Now the oxidation process is the silver, Ag going to Ag plus, right? This thing's going to have a delay. Now why is there a 4 there? Well, actually I got to add something here. Where did I put it to? Okay, good. I like that. Alright, so we've got 1 E minus here, we've got 4 up here, so obviously we're going to have to multiply this whole thing by 4, right, in order to get it balanced. Alright, so that gives you the idea of your 2 half reactions. Now, this is written as an oxidation. On your reduction potential chart, it's going to be flipped, right? Okay, written as a reduction, it would be Ag plus the electron going to Ag. Alright? So those are our 2 reduction potentials we're having to work with. Now, does it matter that we had to multiply this bottom half reaction by 4? Do we change our voltage? Okay, remember the voltage, the E0 is an intensive property. It means it doesn't depend on the amount of moles that we have here in our chemical reaction, okay, chemical equation. Okay, so having done that and made sure that we can kind of match this up with what's on our chart, now we should be able to calculate this fairly easily. E0 here is the reduction process, which is 1.23 volts. And again, that's the reaction of the oxygen plus the 4H plus going to H2H2O. Okay, minus the reduction of the silver, which is 0.80. Okay, so when we subtract those two from one another, we're going to get 0.43. Okay, so because that's a positive E, what would we expect already about our delta G here? It's going to be negative. This is a spontaneous reaction the way that it's written. Okay, so then all we have to do is take delta G0. It's equal to N. Now, this might have been a little bit tricky if we hadn't done the half reactions, but how many electrons got transferred in the course of this reaction? 4, right? Okay, 4 gained, 4 lost. Okay, yeah, you don't add those two together because one side is gaining 4, the other one is gaining or losing 4. All right, so negative 4, and this 4, it would technically be moles of electrons, so we can go ahead and write the moles here, times the F, which, going back over here, F is 96,500 coulombs per mole, or joules per volt times mole. Okay, I'm going to write it that way because I'll show you on this first one how the units all sort of work. 96,000, whoops, 96,500 joules per volt times mole. Okay, times the E0, which we just found was 0.43 volts. Okay, so you plug all that in, and look what cancels here. Our moles cancel, our volts cancel. That leaves us with joules, which is okay for delta G. I mean, typically delta G is in kilojoules, right? So maybe we'll change that at the end, because you are going to get a fairly big number here. So again, this is one of those unfortunate places where, let's say that we are given the delta G and asked to calculate the E. The G is probably in kilojoules, right? And your coulombs are in joules. So you're going to have to convert one or the other if you're solving for E. Now, on this one, it doesn't really matter, okay? Because we can report the delta G in joules, and I don't think they would count you off for that. But we'll go ahead and change it anyway, because like I said, this is going to be a big number. Here's 0.43. 165,980 joules, which to our sig figs, well, there's not really any sig figs in this problem, right? I guess we'll go with the sig figs they give us on the standard reduction potential chart, which would be, looks like 2. All right, so we've got 170,000 joules, which equals 170 kilojoules. Negative on both of those. Okay? So again, watch your signs. If you get to the end and you're like, wait, that's supposed to be spontaneous and my delta G is a negative, then just go back and make sure you handled your signs correctly. Okay? So pretty simple process there. Hopefully that makes sense. Now, suppose the reaction had been written as this instead of the way that it was written on the previous slide. Now, what's the difference between those two? The coefficients are different, and how are they different? They're exactly half of the original coefficients, right? So, the value of E0, is that going to change the value that we calculated here for our voltage based on the coefficients? No, okay? So our E0 is still 0.43, so E0 is going to be the same, okay? 0.43 volts. Because it's an intensive property. Now what about delta G? Okay, probably not the same, but we can do better than that, because if we look back at the equation, what's the part that's going to change if we halve the coefficients? The moles of electrons, right? We're going to have 2 moles of electrons being transferred as opposed to 4, okay? So that means that this negative 170 here is going to be exactly half, okay? Which would be do this negative 85. Is that right? Is that right? You guys don't say anything. Yeah, negative 85. Yeah. You guys need to be better at mental math than I am. Need your help. Alright, so negative 85 kilojoules, okay, which is half as much, okay? Alright, so delta G is dependent on the amount of electrons being transferred. It's dependent on the amount of stuff that we have in the reaction. The E is not, okay? Alright, now we need to talk about concentration and how that affects the cell EMF, okay? Now, I want to be clear about this because this could be a little confusing because I just got done talking about the fact that standard reduction potentials are not influenced by the amount, okay? That is standard reduction potentials because E0, what's part of the standard there? 1 molar, okay? We're assuming these things happen at 1 molar concentration, okay? So in that case, the number of moles don't matter because everything's at 1 molar concentration anyway, okay? That's why E0 is an intensive property. But when we're trying to find the actual voltage of something when the concentrations are not at 1 molar, when we're at non-standard conditions, that's going to have an effect on the voltage, okay? So you just kind of have to keep that in mind. So calculating the E not under standard conditions is very similar to calculating the delta G, which when it's not under standard conditions, okay? So here's how we kind of derive that. You remember this equation from the last unit? Delta G equals delta G0 plus RT ln Q. That's how you get a delta G when it's not at standard conditions, right? But we just said that delta G equals negative NFE, right? And delta G0 also equals negative NFE0, right? So we can actually plug those in for the delta G and the delta G0, okay? So we're just substituting those in. Then we can kind of simplify the equation. If we divide both sides of this thing by the negative NF, then we're going to end up with just E on this side, okay? And then in this first term here, we're going to end up with just E0, right? Now, I shouldn't have crossed that out because that has to apply to both of the terms here, right? So then in the second term, we end up with negative RT over NF times ln Q, because what you end up with there is RT ln Q over the negative NF, and they're just kind of rearranging that, putting the minus sign first, RT over NF times ln Q, right? Now another form of this equation, if we're at 298 Kelvin, assuming that the temperature doesn't change, okay, which is probably a reasonable assumption. If you're doing a redox reaction, usually the temperature doesn't change that much. It's usually the concentrations that are changing. That's what makes it non-standard, okay? But all they're doing there is they're taking the R times the T divided by the F, because those are kind of the three things that are constant if the temperature stays the same. And so you end up with this number here. Now, the V here, that's volts. That's a unit. That's not a variable that you have to, plug in for, okay? So this top number here, that's just a number. So E equals E0 minus this number here, 0.0592 over N times the log of Q. This equation is on your equation sheet, okay? So you don't have to memorize that or understand exactly how to derive it, but you should be able to. I mean, this is not a real difficult derivation, okay? All right, next. So if we look at this reaction here, we've got zinc plus copper 2 plus yields zinc 2 plus copper solid, okay? And we want to know what the EMF for this reaction is when our concentrations are not standard, right? We can look on our chart here and we can figure out the E0 when we have 1 molar Cu2 plus and 1 molar Zn2 plus, okay? But in this case, we do not have that. We have a lot higher concentration of the copper 2 plus and a lot lower concentration of the zinc, okay? So let's just plug this into the equation we just derived over here. E equals E0 minus 0.0592. That's volts divided by N times the log of Q. Okay. Thoughts on maybe the first thing that we need to figure out here? Okay, E0. There's actually several things we have to find in this particular equation, which is a little bit of a hassle. This one shouldn't be too bad, though. E0 here, we're just going to look at the standard reduction potential chart to find that, okay? And the one that's being reduced here is the copper, right? Okay, so the copper is being reduced. The voltage on the copper, or the standard reduction potential for the copper, is 0.34 volts. You might accidentally memorize that one at some point. Minus the zinc, which is negative 0.76. Okay, so that gives us, again, I should be able to do this in my head. Whatever, I just didn't, my calculator was not right. .10. Again, I should have remembered that number from the other day because we did this one several times. Okay, so 1.10 volts, that's our E0. Okay, now what else do we have to figure out here in this equation? We have to figure out our Q, right? Now, Q is just like the equilibrium expression, except we're not necessarily at equilibrium, right? So we're just taking products over reactants. But what are the only things we have to include in our equilibrium expressions? Or our Q expressions? Just the aqueous, yeah, the aqueous and the gases, right? Okay, so it's basically Zn2 plus here over Cu2 plus, and they're both one-to-one stoichiometry, which makes this one nice. All right, so we've got 0.050 divided by 5.0. Okay. So our Q here is going to be pretty small. So our Q equals 0.01. Alright, so now we have everything except for our N, but we can probably figure out our N pretty quickly. How many moles of electrons are being transferred in this particular reaction? 2. Because the copper's going from a 2 plus to just copper, and the zinc is going from a 0 to a 2 plus. Alright, so now that we've got everything, we can calculate our E. E equals E0, which is 1.10 volts, minus the 0.0592 volts divided by 2, times the log of 0.010. Okay, so I'm getting 1.16. Is that right? 1.6 volts. When we take the log of this small number here, you should get a negative number. Okay? I believe that, yeah, this is log of, I mean, you could do that in your head actually, because log of 1 times 10 to the negative second would be negative 2, right? So then you multiply that negative 2 times the 2 here, and you should get negative 1. Okay, so wait a second. Did I mess something up here? Let me double check this. You got 1.16. Yeah, I think that's right. Yeah, that's right. Okay. Yep. I'm thinking myself here. So 1.16 volts, okay? Now, we want to see how this new EMF relates to the EMF at standard conditions. Standard conditions, it's 1.10. Here it's 1.16. Not a huge change, okay? But this is higher, right? EMF is higher. In other words, we get a more spontaneous reaction in the forward direction when we have these concentrations. All right, so let's think about Le Chatelier for a second here. What did we do? Let's say, because at standard conditions we have 1 molar of this and 1 molar of this, and now we have 5 molar of this and there 0.050 molar of the zinc. Okay, so we just greatly increase the concentration of the reactant, which pushes the equilibrium towards the products. Okay, that kind of makes sense, right? We made it more spontaneous in the forward direction by doing this. Okay, so all of these things should work together. The idea of your E, your delta G, your equilibrium constant, all of those things can tell you something about the equilibrium of this reaction. So I guess the answer here is yes. You can write a little bit more of an explanation on that one if you want to. All right. Calculate the EMF at 298 K generated by the following cell, and it's giving us some concentrations here. All right. First thing we need to do here is figure out what's being oxidized, what's being reduced. And I just realized you don't have the chromate thing on your chart. I gave it to you on another set of notes. I'm trying to think if there's anything different about this one than the last one we just did. Because, I mean, essentially we're doing the same thing, okay? Yeah, so let's just take a pass on that one. Pass. All right, I'll write pass. Pass. Or do if you want. I don't want to tell people what to do, you know. All right, so here's a little bit different question, though, because now they're asking us about the concentration of the H+, and they're actually giving us the voltage of the cell, okay? So we've got a zinc H+ cell, and it's 0.45 volts when the concentrations of the zinc and the hydrogen are 1.0, all right? Now, this is not necessarily telling us whether it's at standard conditions or not. It might be, okay? So we kind of have to figure that out first. So first thing that we should probably do here is write the actual reaction that's taking place here. If we have a zinc H+ cell, then what we've got going on is we've got the zinc plus H+. And what is that going to do? Is it going to do anything? If it does anything, what would happen here? We'd make hydrogen gas, right? Now, it's probably going to, because they're giving us the pressure of the hydrogen gas, right? Plus zinc 2+, all right? If the hydrogen is getting reduced, then the zinc must get oxidized. And we know that the zinc always gets oxidized. 2+, and also, here is the concentration of the zinc 2+, okay? So then I need to put a 2 right here in front of my hydrogen to balance the equation. Okay. And we basically just need to figure out, I mean, we've got the same equation going on here, right? E equals E0 minus, I keep forgetting the number, 0.0592. Divided by N times the log of Q. All right. So, yeah, this one's not a ton of fun. I don't anticipate them giving you one that's quite like this. Okay, but we can solve this. It's just a little difficult. We can find our E0 here, and they're actually giving us the E as well. Okay. So we have both of those things in this equation. What we're going to solve for is something within the Q expression, okay, which is a little bit tricky. So the Q here, our Q expression for this reaction would be, I should label my states of matter here to help me out. It's going to be the zinc 2+ times the This is kind of weird because we're sort of mixing them together here. And I'm trying to make sure that I can do that. Let me pause it for just a second here. Okay, sorry about that. Just wanted to make sure that it's okay for us that we don't have to do a conversion here, because we haven't really talked at any point during the year about combining in one equilibrium expression a concentration and a pressure like this, but we're going to go ahead and do that. So our Q here is our zinc 2 plus. Added side effect is that my smartboard seems to have caught up now, so that's good. Let me write this correctly though. The pressure of the H2 gas, okay, divided by the concentration of the H plus squared, right? Because we had a 2 coefficient in front of the H plus in our equation. So, again, if we're looking at our equation here, E equals E0 minus the 0.0592 over N times the log of Q. Let's go ahead and solve for Q first, and then we'll plug that in. I think that's probably the easiest way to do this. So our E here is 0.45. They're telling us at whatever conditions we're at, whether they're standard or not, that's our voltage that we're getting out here. Now our E0 for this reaction, because this is a hydrogen cell, it's going to be 0.00 volts minus the zinc on our standard reduction potential chart, which we just did that on the last one. It's negative 0.76. Okay, so that's going to give us 0.76 volts for our standard. So you can see here, the 0.76 volts is not the same as the 0.45, so we are not at standard conditions here. Something is not at standard conditions. Now, we're at 25 degrees Celsius. We have a 1 molar concentration of the zinc, and we have a 1 atmosphere of pressure of hydrogen. That all looks pretty standard to me, right? So the thing that must be non-standard at this point is the concentration of the H plus. Okay, so 0.76 volts minus, and then we've got this whole expression here, 0.0592 volts over number of electrons being transferred here is 2. Okay, and again, I had to erase the equation, but you guys should have that on your sheets, times the log of Q. Alright, so we can work all of this out here, and we can get log of Q on a side by itself, which would probably be the best thing to do here, and then we'll talk about how to solve that. Just check myself here to make sure. Yeah, 10.47. Okay. So log of Q equals 10.47. Now, how do we get rid of a log, I should say? We 10 it, right? Okay. So Q is equal to 10 to the 10.47. It's going to be a fairly large number here. So then we're going to get, like I said, a very large number here. 2.97. Actually, I guess we need to round to 2 figs here. Or we could just worry about that later, but I'll just go ahead and go to 3.0. 3.0 times 10 to the, what is this? Is it the 10th? Okay, to the 10th. So there's our Q, okay? So now we can plug that in. 3.0 times 10 to the 10th is equal to the Zn2 plus, which we said is 1 molar. I guess I should just, these are activities now, they don't have units. So just 1.0 times the pressure, which is 1.0, divided by the H plus concentration, which is squared, right? So then if we're going to solve for this, we're going to eventually end up taking 1 divided by the 3 times 10 to the 10th. And then we have to take the square root of that number, because we've got H plus squared. So we should end up with a 5.8 times 10 to the negative 6th as our concentration for H plus. 8 goes to the negative 6. Okay? So that's how that works. Now, an easy question they could ask you as a follow-up there is, what is the pH? Right? And all you have to do is take the negative log of the H plus concentration there, and you should be able to figure that out. Okay. The concentration cells, I'll talk about those briefly in class tomorrow, but that's not so important that we probably need to talk about it on the video. Let's skip right to the cell EMF and equilibrium, because we do need to talk about this, okay? And like I said, I'll hit on the concentration cells in class, but I want to make sure we get to the equilibrium stuff, okay? So, by the way, that last equation that we derived called the Nernst equation, okay, just in case you ever hear that referenced at any point, the Nernst equation. So, what happens to the Q in a redox reaction as the reactants are converted to products? So let's just think about this for a second, just in terms of Le Chatelier, in terms of just general equilibrium type stuff. Our Q is going to be, in general, it's products over reactants, right? So as the reaction proceeds in a redox, and we go from the reactants to the products, what's going to happen to Q? Q is going to get bigger. It's going to increase, okay? So then what does that do to the value of E? Again, thinking about the Nernst equation here, E equals E0 minus 0.0592 volts over N times the log of Q. Okay? As Q gets bigger, what does that do to the log of Q? It's not a trick question on that one. It's actually going to get bigger, right? So the log of bigger numbers is going to be bigger than the log of smaller numbers. So as Q gets bigger, the log of Q gets bigger. As that gets bigger, this whole expression gets bigger, right? What does that do to the value of E? It actually causes it to decrease because we're subtracting this term from the E0, right? So the value of E is going to get smaller. It's going to decrease. Eventually, you're going to get to a point where E equals 0, okay? So what happens when E equals 0? At that point, the concentrations on each side are equal, okay? And, well, okay, we didn't really talk about the concentration cells yet. That's okay, you can still understand this. At this point, we are at equilibrium, okay? When E equals 0, we are at equilibrium because now it's not moving spontaneously in either direction, right? Does that make sense? So when E equals 0, we're at equilibrium. Okay? Now that's a useful piece of information because now we can sort of manipulate the Nernst equation or rewrite it a little bit, okay? Because now, this is going to be 0, right? And this log of Q becomes log of K at equilibrium. So, what you end up with here, this equation, and this is a rearrangement of 0 equals E0 minus 0.0592 volts over N times the log of K. Alright? So all we did is kind of rearrange that now, okay, and you end up with N times E0 over 0.0592, okay. I'm not sure if that's the form that equation is written in. On your equation sheet or not. It could be written with the R, the T over the NF in there. That's the other way that you could write this. If you go back to our original derivation before we simplified it to a number, it might be written as E0 minus RT over NF times the log of times the natural log. I feel like that might be a mistake. Oh, no, that was a natural log. Okay, yep, I failed to mention that before. Because this equation is written as the natural log of k because we got that from back here. Right, this is a natural log of q. Okay. This is a variation, and I didn't, point out the fact here that the natural log gets converted to a log. Okay, it's just a different way of writing the expression. So this number is going to be different than it would be if we expressed it in terms of the natural log instead. Okay, but this is a common way to express this. So, it could be written one of these two ways on your equation sheet. I'm not sure which. Okay, probably one of those two. But what that means is, if we know the standard EMF, we can actually calculate the equilibrium constant. Okay, and all we have to do is just use one of these two equations. Probably this one most of the time would be the easiest one to use. Okay? So an example here, using standard reduction potentials, calculate the equilibrium constant for the oxidation of Fe2 plus by O2 in acidic solution. And then it's given us the reaction here. Okay? So all we have to do for this one, E equals E0, nope, sorry, still working with the old one. Because at equilibrium, E is equal to 0. What we've got here is this equation. Is probably the one that would be easiest to use here. Just the log of equilibrium constant is equal to NE over 0.0592. And then all we have to do here is figure out our N. Okay, our N is going to be what on this one? 4 electrons, because we've already done a reaction very similar to this. Okay, the E0, you just have to look on your reduction potential chart and figure that out. Plug those in, and that would be your K. All right. Hopefully that makes sense. We'll have some time to practice this in class as well. Okay. All right. Sorry for the length of the videos the last couple of days. See you guys in class.